problems? Okay, so let's take a look at some practice problems together. You can find these problems on Canvas in the Chapter 15 module. Question 15.39 asks us, for each pair of compounds, identify how you would distinguish them using either proton NMR spectroscopy or carbon-13 NMR spectroscopy. Let's start with A. I think the first thing you would notice in A is that the molecule on the left has two planes or axes of symmetry. It's got one going this way and it has one going that way. So if we think about the number of signals that you would get in the carbon-13, that's what I would use to solve this. I mean, if you look at these four carbons, they are all equivalent. If you look at these four carbons, they are all equivalent. If we look at these two carbons, they're equivalent. And then if we look at these carbons, they are equivalent. So what that means is that in the carbon-13 NMR spectra, we would only see four signals in the carbon-13 NMR spectrum. Could anybody tell me how many signals there would be in the carbon-13 in the other compound? Could anybody tell me how many signals there would be in the other one? And don't be shy to type it into the chat, even if you have a guess, even if you think it's a wild guess. Exactly. Okay, Clinton, that's not an easy question. But yes, Tracy, Clinton, both of you are 100% correct. Not an easy question. But yeah, Clinton wrote 12, and then he put, there's no axis of symmetry. There's no symmetry in this molecule whatsoever. I mean, zilch. Every single carbon in here is unique. Why? Because this carbonyl kind of throws off the symmetry of everything, compared to the first molecule. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see a total of 12 signals. You can imagine that if you pick up a sheet of paper, an 8.5 by 11 sheet of paper, and you look at a big carbon-13, one's got 4 signals and one's got 12, you can tell the difference between those two compounds pretty quickly. Okay, it would only take you seconds to identify that. All right, there we go. Let's see here. Let's try B, and let's take it from the approach of carbon-13 again. Okay, if we look at B, and if we look at the first one, this compound here, hopefully you can clearly see that there is a plane of symmetry going through the molecule like this. In this compound, there isn't a plane of symmetry. No, there's no plane of symmetry. There's rotational symmetry, but there's no plane of symmetry in the molecule. Okay, so if we look at the first molecule, you can see that these two carbons are chemically equivalent, and then this one is unique. So for the first one, in our carbon-13 spectrum, we're going to see two signals. Only two signals. Whereas in this compound, what I want you to realize is that all three of these carbons are unique. Now, why would they all be unique? Let's look at the two carbons here in blue and red very carefully. Why would these two be unique? Think about the environment that they're in. Like, imagine what they're seeing. They're both seeing different things, right? If you think about these two green carbons here, what they see is exactly the same. They both have the same view of everything. But the blue and the red carbon that I have highlighted here, what they see is different. Think about it this way. The one that I have in blue, it sees the fluorine as sticking up, but the one that's in red sees the fluorine is sticking up as well, okay? But the one in blue has the chlorine going down, and the one in red has the chlorine going up. So they're clearly in different electronic environments. and therefore they're going to produce unique signals. It's a little bit trickier, but the idea is that this compound has 3 unique carbons in it. And so in our carbon-13 NMR spectrum, let's pencil this in here, carbon-13, we're going to see 3 signals. Now you might be wondering, what about the proton NMR, Mr. Dion? Well, if we look at the compound on the left, of course, you have protons. You have a proton pointing down here, you have one going down here, and you have one going down here. You're going to see 2 signals in the proton NMR spectrum as well, because these 2 protons are chemically equivalent. So if we put the proton, you're going to see the same thing, 2 signals. We're also going to see the same number of signals as we did in the carbon here. If you look at this proton is going down, this proton is going down, and this proton is coming up. So we have 3 unique protons. And thus, in the proton NMR spectrum, we're going to see 3 signals as well for this one. All right, so you could use proton or carbon for this one. Same thing with this one too. You could use proton and you would see 4 signals and 12 signals. But anyhow, let's move on to C. Could anybody tell me a way that they could distinguish between the 2 compounds in C? There's a lot of aromatic protons here, but there is a big difference between the 2 molecules. Anybody have an idea for C? How you would distinguish between these 2 molecules? Sorry if it's loud, but my niece and nephew are making all kinds of noise.
Could you just differentiate with proton, because the one on the left will have an extra, like another, like proton signal from it being alcohol?
Yeah, I think that's totally reasonable. Yes. I mean, if you look at the compounds, I mean, the compound on the left, so what you're saying is use the alcohol, right? Because in alcohol, you're going to have a signal, you're going to have a singlet that's broad. So we'll put here singlet, broad, between 2 to 5 parts per million. There's no alcohol over here, so you're not going to see it. So I agree with you 100%. That is perfectly correct. And then with this compound over here, what you're going to see is that's not in the other compound is you would have a singlet, you know, that integrates for 3 protons. So we'll put here integrates for 3 protons. So a methyl, you know, that's a singlet. You don't have that in this compound. So I say that's a perfectly good way to do it. And I'll be frank with you. And I see that Clinton put the same thing. Katie put the same thing. That's how I would do it. Honestly, if somebody asked me to do it, that's how I do it. You know, there is another quick way to do it, I would say. Since there's no symmetry in either of these molecules, the compound on the left only has 10 carbons in it. So you would see, let's write it down here. The carbon-13, you'd see 10 signals. But in the carbon-13 of this compound, you'd see 11 signals. The carbon-13, you'd see 11 signals. They're both good ways, but I'll have to admit, if somebody asked me to look at them, I would use exactly what you guys said. Okay, I would pick the same thing. I would just look for an alcohol in one, and I'd look for a methyl in the other. Done. You know, very quick. All right, is everybody with me on that? And if there's any questions, please do not hesitate to stop me. You good with on that one? Get a thumbs up. Okay, cool. Great. Well, let's take a look at the next one. We got a pair of ketones here. I'm going to ask you guys, let's just make this one quick. If you wanted to just use carbon-13, how many signals would you see for the one on the left, your carbon-13? Not a trick question. Exactly. You'd see 3. Okay, it's not 2 because there's 3 types of carbons. You have these ones, the 2 methyls, then you have the 2 methylenes, and then you also have this carbon from the carbonyl. All right, so this one you'd see 3 signals, and then the one on the right. How many signals for that one? Anybody? I know you know the answer. Yeah, absolutely. Absolutely. I knew my students would know. All of my students are 100% correct. There's 5 signals, aren't there? There's no symmetry in this molecule whatsoever. So we'll put that down here. Where's my blue pen? 5 signals. That's faster than I could have done it. So what I'd like to do now is to take a 15-minute break. I would like everybody to try question 15.57, which deals with NMR. It's where they give you some multiplicities and some signals, some multiplicities and chemical shifts. So what this means is this is 1.09 parts per million, 2.12 parts per million, 2.58 parts per million. Then it tells you the integration. Then it tells you the multiplicity. So you have to apply chemical shift. Integration is given to you, and then the n+1 rule, and see if you can propose a structure for this compound, and this one here. And then once you're done with those, I'd like everybody to take a look at question 15.59 and see if you can come up with a structure that matches this molecular formula, but is consistent with the proton and the carbon NMR spectra that are shown here. So again, in this, I'll just kind of go over the first one with you. Oops. If you look at A, this compound has an HDI that's equal to 1. There's no need to draw out the structure. If you have an HDI of 1 and you have an oxygen, then that means that you must have a double bond, either an alkyne, or you could have a ring, or it could be a carbonyl, something like that. But notice that we have 6 protons that are a doublet, and we have 1 proton that is a septet. So that should be a giveaway that you've got an isopropyl group in your molecule. And then here you've got 3 hydrogens that are a singlet. So this must mean that you have a methyl group. Okay. So we have an isopropyl group, which is this part. And then we have a methyl group. So CH3. So I'll put this like this. So that means that we're still missing a carbon and the oxygen, and we're missing a double bond. So you've got this, and I want to see if you can put this together and then try the same approach to B and C. So it's